start the webinar countdown timer now. Greetings to all. I am Daisy, and I will be the webinar moderator. Welcome to the 15th Masterclass Series webinar of the OMS eLearning Academy. Today's webinar topic is octane blending, concept, models, prediction, and measurement. We have an overwhelming response from many countries, and we welcome you all. And hope you all will have a very informational and interactive session today. Before we start, let me discuss a few house rules. The webinar will be 40 to 45 minutes long with a 10-minute Q&A session. You can enter your question in the chat box during the presentation, which will be answered at the end. The webinar will be recorded and available on the OMS eLearning Academy website. There will be a 2-question poll at the end for your input. Please give us your candid feedback at the end via the redirected Google form. We have 2 speakers for this webinar. The first speaker is Dr. Suresh Agrawal, the founder and CEO of Offsite Management Systems LLC and Academy Director of OMS eLearning Academy. The second speaker is Dr. Ariel Kigel, the R&D Manager at UK-based Modcon Systems, Inc. I welcome the first speaker, Dr. Agrawal, to speak at this educational free webinar. About the speaker's organizations, Offsite Management Systems LLC was founded in 1998 in Houston, Texas. Its charter to provide consulting and refinery automation project executions worldwide. OMS eLearning Academy was founded in 2018 to provide continuing education to professionals working in the downstream refining industry and related businesses via the eLearning platform. Modcon was established in 1972 and has been in existence for over 5 decades, marked by profound expertise and continuous innovation in process analysis, control, and AI-enabled optimization. Its mission has consistently focused on enabling the production of high-value products that meet exact specifications, while minimizing costs and reducing environmental impact. This webinar will teach you 3 concepts related to octane blending, concept, models, prediction, and measurement. The first objective is to understand the core principles of octane blending and how different hydrocarbons contribute to achieving optimal fuel performance. Secondly, explore predictive models that help optimize fuel blends by accurately forecasting octane numbers based on component composition. Last but not least, master the techniques for measuring octane ratings, including traditional methods like RON and MON and advanced approaches like near spectroscopy. Thank you all for attending this informative webinar. To appreciate your efforts, we have 2 complimentary gifts for you. Please stay until the end to learn about them. With this, let me request webinar's first speaker, Dr. Agrawal, to start the webinar. I will be back at the end of the presentation. Thank you.
Greetings, everybody. Good morning or good evening, wherever you are. Thank you for attending this webinar, and we have exciting content from myself and from Dr. Kegel. We will start with the basic of octane blending. Now, why do we call octane blending and not as a fuel blending? For the simple reason that octane is a very important property of the gasoline blending. And we have to understand that why is so, why is called, and what is the difference between normal ignition, pre-ignition, and knocking. And to do that, we have to little bit understand the 4-stroke cycle of an internal combustion engine. Then we'll discuss the octane rating for both low and high ranges and how they are calibrated. Understand the concept of compression ratio and the fuel octane required. Identify factor they contribute to higher octane levels. It's just not 95, 94. It can go up to 130, 140 for high-speed racing cars. Then we'll follow the journey of octane through various refinery processes, analyze the octane blend models and its predictive methods, and then address the tangible losses associated with octane giveaways. And we'll review various octane measurement techniques using analyzers. So let's understand, how does the internal combustion engine work? The car can have 4, 6, 8, 12 cylinders, But each cylinder has a 4-stroke cycles of car engine. And it's a start with the intake stroke where it takes the fuel inside, it compresses, it does a power stroke and exhaust stroke. Now the problem is happens with the second cycle, which is a compression stroke. And this is where the problem of knocking and other issues comes into picture. So we have to look at it. What is the cause of compression stroke is critical for the performance of the engine. So there are three aspects of it. In a normal combustion, it is a smooth controlled burn initiated by spark plugs. If it is a pre-ignition, it's uncontrolled, and early ignition may be caused by a hot spot before the spark plug fires. The last one, which is a problematic, is knocking, and it's a multiple spontaneous ignition after the spark plug fires, leading to damaging shock waves. So this is the knocking phenomena that Octane is connected with, and we'll see how it is started. Now, knocking or pinging during combustion is caused by the air-fuel mixture detonating prematurely in the region. Octane rating is a measure of fuel's ability to resist knocking, and fuel is rated for its octane value using reference hydrocarbons. Now, octane is rated between 87 to 130 plus for all fuel types, but the fuel component octane range is only 50 to 130. So different reference hydrocarbons are used for octane rating below 100 and greater than 100. Octane is a quality of fuel components contributed by hydrocarbon structure composition. Let's look at it a little bit more detail. So from the early days after the engine was invented, the 4-stroke cycle invented, the knocking phenomena was observed by the manufacturer as well as the researcher. They were looking for a chemical which can substantially reduce the knocking in there, and they finally found isooctane. So isooctane, the octane rating comes from the name isooctane. That's why it's called octane rating. It's a chemical which has a branches of hydrocarbons, and it has considered as a anti-knocking property and assigned a value of 100 octane. Now, on the other hand, to go to 0 octane value, they use heptane, which is a straight chain and heptane chemical. So between these two, we have 100 and we have a 0. So the rating system uses the percentage of isooctane in a fuel. So for example, if it is a 70 octane or 87 octane, it means that isooctane has a percentage 87 in the fuel mixture and 23% of heptane. So that's how the rating is done for octane. Now, then what about the octane rating more than 100? Now, because isooctane, sorry, this is a mistake. Isooctane has only 100% rating. They use a different chemicals as a reference point for higher octane. So if you see the chart, between 102 to 108, they use ethanol because ethanol has 108 as octane rating. If you go higher than that, 110 to 120, they use isopentane, which is 100, and toluene. And higher than that, they mix MTB with isooctane to go to the up to 130. And the higher octane is used for a higher performance requirement for the cars. So if you look at it, the cars are governed by the compression ratio. The compression ratio is when the cylinder moves to compress the air mixture gas from the original volume to the final volume, it generates the power. So a small car has 8 to 10 compression ratio and it generates 70 to 120 and requires minimum 87 regular. Now, I'm asked a question sometimes that there is benefit to use higher than 87 for the car which requires 87. Really, no. Because why to spend money when you don't need it? So manufacturer always recommended that use minimum 87. If you go to mid-range passenger cars, it's supposed to be used 87 to 91 based on the make and model. And then it goes forward. If you go to racing engine, it uses a 12 to 15 compression ratio, and it can generate 500 to 1000 horsepower power. So based on the compression ratio of the engine, the car octane is recommended by the manufacturer. Now, what is the characteristics of the component, chemistry of the component that imparts low octane or high octane? Now, the characteristic is that if the more branch carbon chains like isooctane, it gives more octane. Aromatic structure like benzene, toluene, and xylene have a higher octane number. Cyclic structures, cyclopentane and cyclohexane. Oxygenate like ethanol. Low reactivity like isooctane aromatic compounds, and molecular size and shape. All these characteristics of hydrocarbon chemistry can decide the value of the octane. And on the left-hand side in the chart, I've given you processes in the refinery which can either significantly increase the octane or moderate increase or slight increase. And based on that, for a blending of fuel oil, it can use a different component with a different octane numbers. Now, this is a typical journey of octane through the refinery lens, I call it. So you can start, say, from 50 to 60 octane for heavy naphtha, or 60 to 70 or light naphtha. And through processing, it can go isomerization or catalytic reformer and convert to 94, 98, 85, 90, 75, 60, so forth. Now, why is it important that we have to have a blend of a low octane and high octane? For example, if you want to make a fuel blending of 87 octane, you just cannot have everything below 87, and you cannot have everything above 87 to make a blend. It has to be a mixture of both low and high octane to make a blend of 87 octane. Similarly for high octane. So you have to have a low and high octane component in the blending to make a desired spec for the blend. In addition to that, there are some butane which are used to control RBP, and also octane, and this 94 and 95. And then also added ethanol in some of the blending. So it gives you a pretty good picture that how does the octane changes starting from crude unit and vacuum distillation unit and end up in the distillation process. So how do we calculate octane? It's more of an art and also a science. Science is a mathematical term. So you start with a linear term. It says take the composition of the component, which is octane value, and multiply its composition, quality and composition. And that's called a linear model. So when I say linear model, the component octane is taken as is. If the component octane is say 87 and composition is 10%, you multiply 10% 87, or below that. It's not changed anyway. But that is not a reality because octane or fuel gas or fuel gasoline has a very interactive phenomenon. There is a nonlinear term. It means if a different component, they interact with each other and they affect the final octane of the fuel, gasoline fuel. Now, how do we correct this nonlinear term? There are two models which are used in the industry or in the downstream refining modeling. One is the ethyl equation and another one is two-port coefficient. Now, both have their own properties, pros and cons. If you look at this closely, the ethyl equation has olefins and aromatics and saturates of the other components. By DuPont coefficient does not have those properties, but it has interactive coefficients. It means it measures that how each component in the fuel blending interacts with the rest of the component. It sort of takes all the properties indirectly for the fuel blending. And you will see, next slide. And then we add the bias term. Why do we add the bias term? Because again, this is not a perfect science. There's always error coming from different processes along the blending processes. So to correct that error, we always use a bias term, which is continuously updated. So give you an idea of a DuPont interaction coefficient. How many are they required? So this is calculated by a combination formula. It means between 1 and 2 is the same as 2 and 1. And if you calculate for a 3-component blend system, you need 3 interaction parameters for 3 components. For 8, it goes to as high as 28 interaction parameters. Now, I did a study for about 14 components, and for 14 components, about 92 to 93 interaction parameters. So the question is that how do we get those interaction parameters? Now, I will not go into too much detail, the methodology to estimate this thing. This is covered in different webinar before this. This is the matrix for DuPont coefficients, and you can see the 14 component, which also includes heal in the final tank. And these parameters are calculated by the equation at the bottom. You can see the huge equations, which is regressed using a multiple nonlinear regression or other techniques. And once you get the coefficients, then you can use this coefficient in the blending model. Now, what do they have the effect? How do we know that what parameters are affecting the interaction or the fuel properties? If you look at this chart, and I have combined the alky in a mixture of alky and butane. On the left-hand side, you can see there is a bonus. It means if you combine alky with the butane, you get a boost in the octane. But on the other hand, if you take alky and some other component, it makes a penalty. Now, there's a little error here. It's not alky, but some other component. So it's a penalty. So you can see, depends on the component interaction, you can have either boost or a penalty. And this is all built in the model. Once you regress the coefficients and apply the model, the final blend property will be calculated accordingly. Now, this is the difference between ethyl equations versus DuPont coefficients method. Now, if you look at the ethyl equations, it both can account for nonlinearity. It can connect the linear model. It depends on the component quality and composition. DuPont coefficients also indirectly relate to component qualities and composition. Blending method is blending values plus bias, and DuPont is a interaction parameter. Now, ease of use, ethyl model is a little bit more moderate, more easier than DuPont model. The reason being that for the ethyl model, you can take the basic generic equation and correct it with the bias term. While as DuPont model, you have to calculate or estimate the DuPont coefficient. It's easier to apply for a specific refinery. For DuPont model is difficult and time consuming. The predictability of blend property is higher for DuPont models. Method of parameter regression, estimation is regression for both, but it requires lab sample also for DuPont model. One of the methods is to use the lab sample, not only method. Both can do online updates and feedbacks, and both use multiple linear regression. Quality is predicted octane and distillation. DuPont only predicts octane. So the ethyl model is a little bit more versatile because it not only can predict octane, but it can also predict the distillation point, 10%, 30%, 50%, 90%. But DuPont, on the other hand, can predict only octane value. Now, you might have heard the concept of octane giveaway, and that's this whole subject of this webinar. Now, if you take 0.1 octane and transfer from regular grade to mid grade or a premium grade, the 0.1 octane is going to give you higher value when you do it for mid grade and premium grade. So there are 4 routes that you are giving away the octane. It may seem very small, 0.1, but look at the economics. So we have calculated the economics of giving 0.1 octane to either mid-grade, premium, or regular. And we have calculated that it's a loss of $26.5 million per year for 275 1,000 barrels per day refinery. Now, that is not a small loss, that's a huge loss. And if you go to higher capacity refinery, the loss multiplies. So that's why the octane blending is very important for a fuel blending. And most of the refineries, if not all, pay attention to minimize this quality giveaway. Now, of course, you cannot violate the octane, but you can give away. And if you choose to give away, you're losing a lot of benefits which can be retrieved. So we have talked about the two ways of ascertaining the octane value, the predictive model and analyzer. In the case of predictive model, there are three methods of predicting it. The first principle blend models, um, uh, which has a hybrid model that I talked about in earlier webinars, and the empirical model. Now, this is a new research which has been coming into trend, that octane can also be predicted by the temperatures, like 10%, 50%, 90% density. Now, there are a lot of research papers which are investigating to correlate this thing and quite successfully. So that's the second method. The third method that I talked about is using a artificial intelligence and machine learning hybrid blend models, where we combine the linear model for quality, which can be blended linearly, and quality like octane, others, which has to be nonlinear blending. So it's a hybrid model. And you can go to the webinar before this one where I talked about this topic in detail. The second method is analyzers. Now, there are three types of analyzer: portable on-site or CFR engine and NIR. Now, CFR engine are used in the lab and also on the offline mode at the blender header, and portable is on-site. Now, this ends my part of the presentation, and I'm going to pass on to Dr. Kegel to talk about analyzers. Ariel, I want to give you the control.
Yes, thank you very much, Dr. Suresh. So I have the control. Let me check just a second.
Yes.
Yes, okay. I can switch between the slides. Okay, thank you. So thank you very much for the introduction. And I will take from that point. So as Dr. Suresh mentioned, there are actually a few methods to measure octane by analyzers. The first one, and you can see it on the left side of the slide, it's portable octane analyzer. The advantage of this analyzer is that it's small, it's portable, you can take it from one place to the other. But this is actually all. I mean, there is no much advantages, and definitely you cannot use this apparatus to measure online. Why? First of all, it takes time to perform a measurement until you get the results, until you feel the volume. And definitely the accuracy of this analyzer is not high because it's based mainly on the spectroscopic method, but it's used a general model, which is not updated. It's a kind of general model which is based on the results that were achieved at from different refineries, and the accuracy of this machine is not adequate enough to control the process. Two other analyzers, and you can see Octane engine and the process near correlative analyzer. These are actually two analyzers that can be used in the process. Octane engine mainly used in the laboratory. It also can be used in some places in the world. It's also used for the online. And we do see the tendency to switch from the Octane engine analyzer, online analyzer, to process correlative analyzers. It can be near, it can be FTIR analyzer. And let's see on the next slide what is actually the advantages and disadvantages of each one of these methods or analyzers. Okay, so first of all, when we are talking about Octane analyzer, discrete Octane analyzer, it means that this analyzer is working exactly according to the ASTM standard. The main advantage of that is that we know what is going to be the accuracy of this analyzer. and the quality of the measurement of these analyzers, it's actually not depending on the feed quality. So we know exactly what is going to be the accuracy of this method. But besides that, this analyzer is also provides us a very good correlation to the laboratory. Why? Because laboratory is using exactly the same method. The disadvantage of this analyzer that it has a longer response time compared to the correlative method analyzers. It takes a few minutes until we get a result. And sometimes when we're talking about very fast processes like gasoline blending, where we would like to get a very high accuracy of 0.1 octane, sometimes it's not enough getting a result once a few minutes. And definitely the most problematic disadvantage related to this kind of analyzers, it's actually the maintenance. You can see definitely on this picture, it has a lot of moving parts, engines and machines, and maintenance of such an analyzer estimated of something like $50,000 per year and higher. The second type of analyzer. Okay, so the second method, or the second analyzer, is a process near correlative analyzer. I'm going to introduce near analyzer, but when we're talking about the correlative analyzers, it can be near analyzer, it can be IR analyzer, it can be FTIR analyzer, or it even can be NMR analyzer. And when we're talking about the correlation, it means that we are not measuring directly the property of interest, but we are measuring something else. In our specific case, this something else is an absorbance spectra. And we find a correlation between the absorbance spectra and the property of interest. Having this information, we build a mathematical model. A mathematical model which explains the correlation, mathematical model in our specific case for octane number. And we use this mathematical model in order to predict results. Okay, this is actually what are correlative method analyzers. So what is the advantage of this type of the analyzers? First of all, it's low cost of the ownership. And when we're talking about low cost, it's have to be compared to some other methods. The other method is definitely octane engine. And this analyzer has a very high advantage over the octane engine because it also can measure additional properties of interest which are required in order to characterize, in order to pasteurize the final product, octane or diesel or jet fuel. There are actually a long list of additional properties of our interest, not only octane number, but also chemical composition. Like if we're talking about gasoline, like olefins, like benzene, physical properties like density, rate vapor pressure, distillation points, T50, initial boiling point, final boiling point. Okay, there is a long list of different properties that can be measured by the same analyzer. In addition to that, this analyzer also have multi-stream capabilities. It means that if we are talking about the gasoline blending header, and sometimes many customers have few of such headers. For example, one blending header which is used for blending low octane gasoline. The second header which is used for high octane gasoline, and maybe one additional for diesel blending. So this analyzer can actually cover few heads, few streams. And generally speaking, if we would like to talk about the optimization of the process, we can also provide the quality not only for the final product, but also for the components that are being used for the blending. Once we have this information, we can deliver this information to the process unit. in order to provide them with some recommendations. For example, reformate. Your reformate now is octane of the reformate is too high. We don't need so much octane. You can make changes in the process and to lower the octane number, okay, and so on. So additional advantages, expensive and time-consuming laboratory analysis are no longer necessary. We have online analyzer, which provides us with a lot of data about our process. Each few seconds, we have information, what is happening with our process. Minimum maintenance required for this analyzer. Again, compared to the ASTM engine, there is no moving parts inside. The one and the only maintenance that may be required is replacing the light source once a few months, and maybe filter as a part of the sampling system, but it's something which is used to be done once a few weeks maybe, and so on. So when we're talking about maintenance, it's much easier, it's much cheaper. And in addition to that, there are also a lot of different supporting software that allows us to increase the quality of the measurement, to maintain, to build, to update the mathematical model, and we will talk about it a little bit later. So as I already mentioned, this specific analyzer that you can see here has capability to measure multi-streams, in this specific case, up to 8 streams per analyzer. The biggest advantage of this method, this specific analyzer, is that the measuring cell can be located at the distance of 3.2 kilometers far away from the analyzer itself. What does it say? It says that the single analyzer can actually cover the area of 9 kilometers. It means that we can measure completely different processes. We can measure, let's say, gasoline blending, and we can measure diesel blending, which are located far away from each other, using standard telecommunication fiber optics, which enables us to measure for such a long distance, and also very cheap. As I already mentioned, such a method analyzer contains no moving parts and field units, measuring cell, sampling system. It contains no electricity, so it can be easily installed under the explosion environment, even zone 0. So what is actually absorbance, and how we get from measuring absorbance or getting the spectra of absorbance to the real properties of interest, octane number. If we can measure the intensity of the light which enters the measuring cell, and we can also measuring the intensity of the light which coming out of the measuring cell, we can actually characterize the sample which is located inside of our measuring cell at this specific time. So having this information enables us to build a mathematical model. In order to build a mathematical model during the calibration phase, we need two things. We need a spectra from the analyzer, and we need data from the laboratory which characterize exactly the same sample. So we have few samples, we have spectra from these samples, and we have laboratory data for these samples. Having this information enables us to build a calibration model. Once we have a calibration model, we move to the measurement phase. We upload this mathematical model to our analyzer, and each and every new spectra, new sample which enter the measuring cell is being measured. We measure absorbance of this sample. And once we have a mathematical model, calibration model, we multiply the spectra with the model, and we get a property of interest. In our case, it will be octane number, but we can also build models also for the other properties, as I already mentioned before. So when we are looking at the absorbance spectra, we are not looking at the peaks. Definitely peaks provide us with a lot of information, but we are looking on each and every point of this spectra. And when we have this information, we take this information and we build a matrix. And you can see an example here. Each and every row in this matrix is actually a different spectra. If, for example, we have 20 samples, we have 20 spectra, we will have a 20-row matrix. The second matrix that we are going to build is matrix which contains information from the laboratory. So we have information about octane number. Maybe we also have information for other properties. For example, benzene, olefins, or density. Each and every column in this matrix will contain information about the property of interest. Once we have these two matrices, we multiply one of them on the other, and we get a mathematical model. And here you can see how the mathematical model for a octane number is look like. Mathematical model is actually a vector. And here you can see universal model for octane, gasoline octane. In this specific case, it's MON, machine octane number. And this mathematical model consists built based on something like 100 different samples. It's very important to mention here that in order to build a mathematical model, we don't ask from the end users, from our customers, to provide us with the information of 100 different samples. Why? Because it may take a lot of time, it may take a lot of efforts, a lot of investment to collect all this data. What is actually done? We actually use models from our database, from the similar projects, similar processes. And what we do else, we're actually making a localization of the model. We update this existing model from the library with the samples from the current project. And the standard practice says that it's enough to have something like 20 samples from the process in order to get a high quality model which describe the process of interest. This is actually what we call a model localization. We were talking about the neural analyzer and its advantages, but besides its advantages, we also have a few disadvantages related to this analyzer, related to this method. First of all, its environmental and operational variability. Definitely the environmental temperature can affect the results, but it's something which is easy to solve. Analyzer provided with environmental enclosure. In this specific case, it's even much simpler because the analyzer can be installed in at safety area, in equipment room, in control room, where we have air condition, where we have a controlled environment. This method also have high dependency on the reference method. It means that in order to build a high quality mathematical model, there is a need to have a high quality data from the laboratory. It's very important during the model building procedure. Definitely, each and every model, not talking about the process analyzers, but also models for the advanced process control refinery units, they have a degradation over the time and have to be updated. And on the next slide, I'm going to present a few software solutions based on the artificial intelligence and the machine learning tools that are used in order to keep the models constantly updated. So one of the software which was developed in order to keep the process of model update in automatic regime, software which is called FreeTune. How this software is work? Analyzer itself is connected to the internal refinery database, which have data from the laboratory. Once a new result from the laboratory appears in the internal database, it's usually LIMS system, these results have to be delivered to the analyzer. Analyzer takes this result and compares it with the historical data For example, today morning, we got a new results from the laboratory for the sample, which was collected 2 days ago and measured yesterday. So analyzer takes this data, going to the historical data of his measurements 2 days ago for the exact timestamp, and compares the data. If it see that there is a very high discrepancy between the data, it uses the laboratory analysis, it uses the laboratory data as a reference. It means it takes the mathematical model and updates the mathematical model with the new data which was received from the laboratory. Definitely, it's not a direct straight process. There is a lot of filters which checking the accuracy of the data that was received, because there may be some mistakes were made by the operator, which decided to enter a value of 97 octane, but by mistake put a value of 9.7. Okay, so there is a lot of filters, a lot of testing that have to be done by the software in order to validate the data which is being used for the model update. So this software takes this data and perform an update of the model. It can be done in automatic regime without any need for the manual model updates. And here you can see a few examples. One of the examples, you can see a mathematical model which was built for the cloud point, and you can see data for 3 months from February to April. During this period of time, the raw material, the crude oil, was changed. What we usually expect when the raw material is being changed, we usually expect that the mathematical model will require an update, because the chemistry of our sample was completely changed, and we will need to update the model. In our specific case, and you can see this on the slide, you can see the blue dots, actually laboratory analysis, and the green line, it's data from the online near analyzer. And you can see a very high accuracy, means despite of the fact that the raw material was changed twice during this period of time, we have a very good correlation between the laboratory data and the analyzer. A few additional examples. Here you can see a bias which was opened between the laboratory data and the online analyzer. And using this software, FreeTune software for the automatic model update, this bias was actually closed. So we again have a very good correlation between the laboratory data and the process analyzer. And on the down side of the presentation, you also see that the bias, the example with the bias, positive bias and negative bias. And also in this case, we do see a very good correlation between the results of the laboratory and results corrected by this software. Besides the fact that we do have software for the automatic models update, sometimes customers don't have adequate infrastructure for automatic model update. For example, they don't have internal database, they don't have LIMS systems, they cannot provide online information for the model update, or in some cases, they prefer to have a full control over the modeling procedure. They prefer to do it manually by themselves. Until now, the common way for mathematical models built or update was using a third-party companies, usually manufacturers or suppliers of the equipment. This process was very complicated. There is a need to have a budget for the models update. Budget have to be approved, ordering procedure, then sample collection process based on the instruction from the service provider, delivering data, model building procedure. As you can see, a lot of efforts and budgets being used in the process, and it definitely takes a lot of time and a lot of money. Alternative option to build models by your own is to keep a modeling team, a team of chemometrists, mathematicians. But since a process of modeling is not a full-time job in many cases, even if such a team was created, it didn't stay long. The option of having a tool for easy model building process was recently released to the market. Artificial intelligence-based tool takes in advantage critical decision that usually taken by model building specialist. And I'm talking about selecting data for calibration and validation, data pre-processing, building a model and analyzing results, detecting and removing outliers, and definitely rebuilding the model and analyzing the results. Everything I've mentioned until now, the software, everything that was mentioned before the software was released to the market was done by the modeling specialist, and operators without chemometric experience have difficulty to process this kind of data. Software, which is called Model AI, enables personnel without any basic skills to build accurate and high quality models. All they have to do is to bring spectra and data from the laboratory and let the software to process the data. Software also useful for advanced users and enables them with the tools where they can take and intermediate decisions in the model building process. For example, they can choose what data will be used for calibration and validation, choose data pre-processing type, detecting and removing outliers. Software also enables them to rebuild the model and make correction. Now we actually come to two last slides. Just to summarize again the process of the data collection and using this data for the real-time monitoring and updating. So the first step is data collection from the process analyzer and laboratory. Both these have to be required to build the mathematical model. Then the model is built using a standard multivariate methods like PLS. It can be done in manual regime or semi-manual using AI tools like Model AI software. Then model validated against the laboratory analysis that is also can be used for FreeTune software as a machine learning tool for automatic model update and correction. Then advanced process control uses online data for predictive control. And as a final stage, data is being used for continuous study and improvement. Just to summarize the presentation, Octane is one of the most important parameters required for the efficient process control. Octane economics related to losses and giveaways was presented during the presentation, and the importance of precise octane measurement was discussed. There are few methods that can be used for efficient octane analysis, and those also were presented during the presentation. Machine learning and artificial intelligence-based software were found as very efficient tools for mathematical models update required for the efficient operation of process analyzers and accuracy maintenance.
Hello, Dr. Suresh.
Yes.
I made two questions to Ariel. I write it in the chat. Can they be answered now?
give me a second, let this finish.
Okay.
Then
Yes,
we can
yes. I can see the questions now. The first question, how much blend data do you need for initial model of NIR? So as I already mentioned, in order to build a good quality model, there is a need for something like 100 different samples. In most cases, manufacturers of the equipment, they already have a database from the previous projects. Definitely those with a lot of experience and analyzers being manufactured for many years. So the standard procedure is to use data from the previous project, similar project, if we're talking about the gasoline blending and we're talking about the octane number, machine octane number, is to use the machine octane number from gasoline blending for the same accuracy, for the same rate. For example, if we're talking about octane of 98, okay? So there are specific components which are used. So it's actually to use the same data from the previous project and to make localization, to add new samples for this existing model to make it accurate, much more accurate for the specific project. In this specific case, there is a need for something like 20 samples only. And the second question, the FreeTune software could be used with other vendors like ABB, NIR, or Top NIR. The answer is not. It was developed, this software, if we're talking about two software, first software, FreeTune software, was developed by Modcon Systems, and it can be used only for the Modcon analyzer. But if we're talking about the second software, Model AI, this software also was developed to support other manufacturers. It means it can be used not only for the Modcon-based analyzers, but also the analyzers from other manufacturers. So I believe the question will be definitely not the automatic correction, not the FreeTune, but if you would like to make the process of model maintenance and model update by your own, not involving third-party companies, you can actually use the software, Model AI, and you will have all the power to maintain the models by yourself without involving manufacturers, without involving third-party companies.
Thank you.
Any more question? No. Then we'll move to next slide. While you are taking the poll, I have two questions here from Pravina. We are interested in to understand an online analyzer-less blending using AI ML. There was a webinar that I did before this one, webinar number 14, on the subject. You can sign on our academy and view the recording. And if you have more question, you can ask me. Second question is from Rika Tiwari. Is AI ML used for model build only, or can we use alternate to analyzer hardware itself? Well, that's a theory which is trending now in the research arena. Or it can be supplement the analyzers online, which Dr. Kegel just talked about it. So it's a combination of both, and it all depends upon the refinery, their infrastructure of analyzers and the model building. And that is also discussed in the webinar I talked about, the one before that, webinar number 14. Thank you very much, everybody, and we hope to see you next time.
Thank you, Dr. Agrawal and Dr. Kegel, for a wonderful presentation. We have now concluded our presentation for Webinar 15. Our Academy has offered monthly webinars on fascinating subjects related to downstream refining operations. Lost tangible benefits in refinery operations, ignorance or indifference? It will be the 16th webinar in the Master Series on November 20th, 2024. Dr. Agrawal of OMS will present the webinar. This webinar will identify the tangible benefits often overlooked or lost in refinery operations, emphasizing these missed opportunities as financial and operational impacts. We will examine real-world case studies to uncover whether these losses are due to a lack of awareness or a culture of indifference, and how both factors contribute to ongoing inefficiencies. Participants will gain insights into the role of advanced technologies and process optimization techniques in reclaiming lost benefits, with a focus on AI, machine learning, and real-time data analytics. The session will also explore strategies for overcoming organizational barriers, fostering a culture of continuous improvement, and ensuring that refinery operations are both efficient and profitable, and the strategies to recover them. Remember to set up an account on LinkedIn. We are beginning registration on LinkedIn on November 1. We will now begin the question and answer session. You can email us any more questions at the email address below and the ones you posted in the conversation. We will ask you 2 poll questions with single and multiple choices for candid comments following the Q&A session. Would you kindly take a moment to respond, multiple choice and single choice questions? First, which factor do you believe has the most significant impact on the octane number in fuel blending? Second, how confident are you in the predictive accuracy of near spectroscopy for determining octane numbers? We will now begin the poll. We will close the poll now. Thanks for participating in the poll. Your answers will give us insight into our webinar content. Our complimentary gift is an ebook with 250 plus pages after you complete the survey. We provide a free 1-hour consultation with our academic director, the webinar presenter, Dr. Suresh Agrawal. Please take advantage of this chance to talk to him about any problems you are having in your refinery, or how to sign up with our academy to receive the benefits of learning. We hope to see you at the upcoming webinar. When you exit the webinar, it will lead you to the Google survey form where you may provide us with insightful comments. Thank you, and have an excellent remainder of your day or evening.